It was all about the uniform continuity of a function. Now, let us see here is another concept which is called homeomorphism, okay, and equivalent matrices. So, homeomorphism means if you have a function f from a metric space x to a metric space y, then this function is called homeomorphism if it is bijective, that is, if it is 1, 1 and onto, and the function is continuous and inverse is also continuous. So, you can say that if function f is homeomorphism from a metric space x to a metric space y, if it is continuous, its inverse is continuous, and it is 1, 1 and onto. And if two matrices x and y are said to be homeomorphic if there exists a homeomorphism from x to y. Take the examples. Suppose let the closed interval 0, 1 and the closed interval 0, 2 be two metric spaces with the usual metric, and define a function f from 0 interval closed interval 0, 1 to closed interval 0, 2 by f of x is equal to 2x. Then you can see that this function is 1, 1 onto, okay. The function is because f of x is equal to 2x is continuous, the inverse image is also continuous, and then f is a homeomorphism and the space closed interval 0, 1 and closed interval are homeomorphic. Take another example. Suppose x is the open interval 0, infinity and y is equal to set of all real numbers with the usual metric, okay. And f is defined as f of x is equal to ln x. Then f is a homeomorphism between x and y. Now take another example. If R, metric space R with the usual metric, is not homeomorphic to the metric space R with the discrete metric. So if you change the space is same, R with respect R with the usual metric space and R with the discrete metric space, they are not homeomorphic. That is to say, you cannot find any function which is continuous and whose inverse is also continuous. Okay. Now let us recall that a function f from x to y, from a metric space x to a metric space y, is an isometry if the distance between fx fy is equal to distance between xy. Okay, and it is obvious that an isometry is 1, 1 and uniformly continuous. And recall that the set x and y are said to be homeomorphic if there exists an isometry between them, that is onto. Then an isometry is necessarily a homeomorphism, but the converse is not true. Okay, so you can see in the previous examples, in these examples a and b, here is this function and this function, two functions, okay, mappings are homeomorphic but not isometry. Now, if the function f is bijective from a metric space x to a metric space y, then the following statements are equivalent. What is this? That is, f is a homeomorphism if and only if G is open, if and only if the inverse f of G is open in Y. It is equivalent to f, capital F is closed if and only if image of capital F under F is closed in Y. So these three are equivalent conditions. So here is, you see that we have seen that if the function is continuous, okay, then the image of open set may not be open. If the function is continuous, then the image set of closed set may not be closed. But if the function is homeomorphism, then the image set of open set is open and the image set of closed set is closed. Okay, so here is we have, so let us prove that these three statements are equivalent. So first we will prove that A implies B. That is, assume that F is a homeomorphism. Okay, F is a homeomorphism means F and F inverse both are continuous, and therefore for any open set G, F inverse, so let us consider this F inverse. So inverse of this F inverse, okay, is equal to F of G. But because G is open, so the inverse image of F inverse is, so this is open because F inverse is continuous. So this function is continuous. So inverse image of open set is open. So this is open. So F of G is open in Y. So this is open in Y. Prove the converse. Suppose F of G is open in Y. Then by the continuity of F, okay, operate F inverse F of G is equal to G. So inverse image of open set, this is open, okay, this is your open, and inverse image of F open set is open, and therefore G is open. Okay, so this is very simple. Now let us prove B implies C. B implies C is again very simple because just we will use the complement of open set is closed. So let F be a closed set, then the complement of F is open, and so by B the image of complement of F is open in Y, but F of capital F is equal to the complement of F of complement of F, and hence this is your open set, so this set is your closed set. And for the converse, let us take this set is closed, then the complement of this is open in Y, and then the image of complement of F is equal to the complement of F of capital F, and this is your open set because this set is closed, so this is your open, and so by B this F of X is open and hence F is closed. Now take the C implies A. So C implies A means this implies this one. So let F be a closed subset of X, then by hypothesis F of F is closed in Y. Since this implication holds good, F inverse F of F is equal to F, the inverse image of closed set is closed and therefore F is continuous. And now since F inverse F is equal to F of F, so by hypothesis F is closed in X, so F of F is closed in Y, and hence F inverse is continuous on F, and therefore F is a homeomorphism. As in case of the continuous function, the composition of continuous function is continuous, composition of uniform continuous is continuous, and similarly here is if X, Y, Z are metric spaces, and if X is homeomorphic to Y and Y is homeomorphic to Z, then X is homeomorphic to Z. So this is very simple, we can prove very easily. Now we can define the open and closed mappings. So how we can define the open and closed mappings? And we have seen that the image of open set is open if the function F is homeomorphism. Okay, so let us take X and Y be metric spaces and a function F from a metric space X to a metric space Y, and this function is said to be open if the F of G is open in Y for every open set G in X. That is to say, a function from a f from a metric space X to a metric space Y is open if image of open set is open, and this function is closed if the image of closed set under f is closed. So the function is f from X to Y is open if image of open set under f is open, and it is called closed if image of closed set under f is closed. So a bijective function f from X to Y is closed if and only if it is open. So very interesting. Indeed, if f is closed bijective and G is your open set in X, then the complement of G, okay, the complement of G is closed in X, and therefore the image of closed set is closed in Y. And since f is because f is closed, but the bijectivity means that the f of G complement is equal to the f of G whole complement, which means that this f of G is open in Y, being the complement of a closed set, and hence f is an open map as well. Now, we have the remark which says that if X and Y are metric spaces, then a continuous and open mapping may not be a homeomorphism. Only a continuous and open mapping, okay, may not be a homeomorphism. Of course, if it is homeomorphism, then it is continuous and image of open set is open, so it is open. So if the function f is homeomorphism, then it is continuous as well as open, but a continuous and open mapping may not be homeomorphism. Similarly, a continuous and closed mapping may not be homeomorphism, but again a homeomorphism mapping is closed as well as continuous. Okay, a continuous and closed mapping may not be open. Okay, the third thing is a continuous and open mapping may not be closed. Again, we have several exercises, okay, related to these homeomorphism. So as we have seen for the several characterizations of a continuous function, similar characterizations we have here, okay, for a homeomorphism. So suppose f is a function from a metric space X to a Y, or f is a bijective function from X to Y, then the following are the characterizations for a homeomorphism. So f is homeomorphism. Okay, this is equivalent to say that the image of closure of A is equal to closure of f of A for all subsets A of X. The interior, okay, the image of interior of A is equal to interior of f of A. The inverse image of closure of B is equal to closure of f inverse B, and f inverse interior of B is equal to f inverse B interior. And for every sequence x in X and for every point x in X, the f of xn, okay, in Y converging to f if and only if x converges to Y. Now, as I mentioned earlier, that the characterization for the continuous function is what? Continuous function means f xn converges to X implies f of xn converges to f of X. But this implication does not hold. But here is what? Here is that if the function is homeomorphism, okay, if the function is homeomorphism, then we can say that this implication also holds good, because the inverse image. So, the sequence f of xn converges to x if and only if this is true. So, if the function is homeomorphism, then xn converges to x if and only if f xn converges to f of x. So, this is the you can see these are the characterization, and they can be proved very easily. Okay, so you can prove this very easily. Okay, now let's take another exercise which says that the unit circle in the usual metric space R2. Okay, so S1 is the unit circle in the metric space, and define a function f from the closed interval 0, open interval 2 pi to s by f of theta is equal to cos theta sin theta. Then prove that f is continuous and bijective but not homeomorphic. That is to say, you will have to prove that the inverse of f is not continuous. Okay. Then here is you can see that, as I mentioned, that if x, y, z be metric spaces, if x is homeomorphic to y, y is homeomorphic to z, then x is homeomorphic to z. And this here is it is the proof, very simple, and you can do it by yourself. Now, show that the function f from x to open interval 0, 1 defined by this one, f of x is equal to x upon 1 over mod of x for all x is in R. This is a homeomorphism, and also show that f is uniformly continuous. You can see that this function, because here is f of x is equal to x upon 1 plus mod of x. So, if f is greater than 0, then the value of the function is this one. If x is less than 0, then the value of the function is this one. And then you can see that you can define the inverse function g in this way. Okay, so the inverse of this function f would be this function. Okay, so how do you get? These things are given over here, and this function is again is continuous. So inverse and therefore this function is continuous. Okay, so therefore, and of course is 1 1 and on 2, and therefore f and its inverse g both are continuous. So f is your homeomorphism. And now here is I have mentioned that how it is uniformly continuous. So you can do by yourself. If you could not find the answer, please check over here. Now show that the image of a complete metric space under homeomorphism need not be complete. Okay, so here is a exercise, and show that the image of a complete metric space under a 1-to-1 uniform continuous function need not be complete. So you can see the function in this interval which is both homeomorphism and uniformly continuous, and R is complete, but the image of R is -1 and 1, which is not complete. Okay, and then here is the exercise. Give the example of a continuous open map is not homeomorphism. Give an example of a continuous closed map which is not homeomorphism. Give an example of a continuous closed map which is not open. Give an example of a continuous open set which is not closed. So here are several examples I have mentioned, so you can do by yourself. Now, if x and y are metric spaces and x cross y is the product of the metric spaces with respect to the metric defined in this way, and if p1, px, py are the projections on x cross x onto x and y respectively defined in this way, then show that the projection maps Px, Py are continuous and open but not closed. Okay, so here is this will give the answer of this question. Open this are continuous and open but not closed. Okay, continuous and open but not closed. So here is you can get and similarly show that the identity map this from the usual metric space R with the discrete metric space is continuous but neither open nor closed. Now again I have another example which says that another exercise. So if F is a map from a metric space X to a metric space Y is continuous and onto, okay, and G composition F is open, then G map from Y to Z is also open. And prove that if G from Y to Z is continuous and injective and G composition F is open, then prove that the map F from X to Y is open. Now here I have a indicator function. Okay, so let us define the indicator function. So an indicator function, or it is also called the characteristics function of a set A, is defined in the following way. The indicator, the chi of Ax is the value of chi of Ax is equal to 1 if X is in A, otherwise it is equal to 0. Okay, and then if A is a subset of a metric space, then the indicator function of the set A is continuous if and only if A is closed as well as open. So here is A is closed as well as open, and this you can see very easily, is not very difficult. So let us move to the another exercise. Assume that the metric space XD is not compact. Then prove that there exists a function f from X to Y which is continuous but not bounded. Okay, so in the next talk, so I stop over here, and in the next talk I will see the equivalent matrices. Okay, thank you very much.